MS Ramaya University of Applied Sciences.
Dear students, we have the flame propagating experimental setup in order to conduct two different experiments. The first experiment is on demonstration of different types of flames with Bunsen burner, and the second experiment of measurement of laminar flame speed. Since these two experiments fall under combustion category, we are doing the two experiments simultaneously, one after another. Let us first consider the demonstration of different types of flames with Bunsen burner. The aim of the experiment is to demonstrate different types of flames with Bunsen burner. The objectives of conducting this experiment are to describe the details of the experimental setup, fuel line, air path and instrumentation, to demonstrate various flames like premixed, diffusion, laminar, turbulent, lifted flames and blowout condition, to relate the flames from Bunsen burner to flames from various other combustion applications, to discuss the associated fundamentals of combustion. Before achieving the objectives, let us start with introduction to Bunsen burner experiment. One can perform few experiments with Bunsen burner, invariably we can say. Various experiments with Bunsen burner can be considered to be first set of experiments in combustion. On the other hand, combustion means burning of fuel with oxidizer to release heat energy. In this experiment, LPG is a fuel and oxygen in atmospheric air is oxidizer. Eventually, with this experimental setup, one can demonstrate premixed flame and diffusion flame, laminar flame and turbulent flame, attached flame and lifted flame. Before demonstrating different types of flames, let us discuss principles and requirements of combustion for various applications. Generally, we refer burning of fuel as combustion. Mainly, it gives heat energy and light. It has wide application, ranging from cooking of food to rockets used in space application. Let us elaborately see various applications one by one. The light created from a lamp has significant importance. Traditionally, it is represented for knowledge and bringing good things since it removes darkness. Hence, lighting a lamp is one of the remarkable event in any function and also daily event in prayer room of a home or temple. Apart from traditional values, oil lamps and candle lamps were extensively used in olden days to get light. Further, hurricane lamps and petromax lights are useful to provide lights and used extensively before genset or generator set is not common. One can describe that in almost all the cases, the fuel and air is separate and the flame is of diffusion flame, meaning that air and fuel diffuses to form burnable mixture in the flame region. Before discussing details, we will see additional applications. Here, we can see use of combustion by and large in cooking application may sometimes useful in living space heating. In the first row of picture, we can see the fuel is of solid in nature, either from wood or coke. Note that the color of flame is of red, orange, yellow, and some cases white patch in yellow zone. In the second row, we have kerosene stoves. These are example for liquid fuel burning. In case of wick stove, the kerosene gets evaporated from the wick mixes surrounding air from atmosphere and form blue color flame at the bottom and light yellow color flame at the end. In other kerosene stove, hand pump is used to send pressurized air in the burner to get good spray of kerosene from combustion. By this, faster burning of kerosene is possible as compared with wick stove. Similar principle is applied in liquid fuel combustors. Third row shows LPG gas stoves. The burner design is in such a way that it gives blue color flame. The blue color indicates that sufficient amount oxygen is already mixed with fuel. If you do not see orange flame form, burner mouth or the top of blue flame, then by and large we can say that the combustion is complete, meaning that no fuel is left out. Nowadays, mostly we use LPG gas stove. One end we saw general application of combustion in day-to-day activities. Let us see the other end of high-end technology of rockets. Here, we see rockets, missiles, and high-end air-breathing engines such as ramjets and scramjets. Rockets are aerospace vehicles to launch satellites. Here, we see rockets with bulk of flame at the bottom. The middle figure in the first row shows the cut sectional view of typical solid rocket motor. Propellants, both fuel and oxidizers, are packed in the combustion chamber. When ignited, the start burns and large volume of gases form of producers of combustion is released. The nozzle helps to accelerate the gas velocities to supersonic speed. You can also see shock diamonds in middle picture of second row. The release of product of combustion pushes the rocket in the forward direction. One can have liquid rocket motors for space applications. The last picture in the second row shows ramjet engine. Here, the oxidizer is air and comes from atmosphere. In the ramjets, the combustion takes place with bulk of air with subsonic speed. In case the mean air velocity enters the combustion chamber is at supersonic, then we can say the engine's scramjet, meaning that supersonic combustion ramjet engines. With the scramjet engine, one have a flight speed Mach number of about 4, calling as hypersonic air-breathing vehicles or scramjets. Missiles used in defense applications mostly works on rocket or ramjet principle. Solid rocket motors, missiles, liquid rocket engines and scramjets makes India to be proud in front of international community. After seeing one end of cooking application and other end of high-tech such as rockets, missiles, ramjets and scramjets, let us see more general use in engineering. Here you can see another best example in internal combustion engines. Internal combustion engines are extensively used in two-wheelers, cars and related light-duty vehicles, bus and related heavy-duty vehicles, diesel engine trains, military tanks, ships, propeller-driven aircrafts, etc. It is of reciprocating type engine. The atmospheric air-fuel mixture in the case of petrol engine or air in diesel engine is sucked inside the cylinder during intake or suction stroke as piston movers from top dead center to bottom dead center. If compressed during compression stroke as the piston moves from bottom dead center to top dead center. Before end of compression stroke, either spark is generated in petrol engine or diesel is injected into the cylinder in diesel engine. Because of this action, the heat is released because of combustion process. Various parameters are important to achieve desired performance and emission level. The heat energy is converted to work as the piston moves from top dead center to bottom dead center. and then the product of combustion is sent out during exhaust stroke, where the piston moves from bottom dead center to top dead center. The cycle repeats and produces one power stroke for every 4 strokes or 2 revolutions. Various types of internal combustion engines are available. Internal combustion engines serves as important power source for automobiles, propeller engines and ships. The purpose of discussing the engine here is one need to imagine or think how the combustion takes place in petrol or diesel engine. The other form of combustion application is on gas turbine engines. The process sequence is somewhat similar to IC engines. However, here the power is generated continuously. The air is sucked through compressor blade passage and fuel is injected into combustor. We can see the flame formation and the exhaust gas is used for rotation of turbine. The gas turbine engines are extensively used in aircraft applications apart from power generation. Let us see another important application of combustion in thermal power plants. Coal is generally used as a fuel in thermal power plants. One can see photographic view and demonstrative sketch of thermal power plant here. In high capacity plants, the coal is crushed into powder form and burned into tangential firing. One can see the burner in the second row and typical flame pulverized coal firing. One can also fire the coal in a fluidized bed form. The flame structure is shown in right-hand side, last figure. In general, fluidized bed combustion and pulverized tangential firing are examples of solid fuel firing, and predominantly coal is used as fuel. As one can combine gas turbine and steam turbine to get better efficiency, combined cycles were developed. Here, we can see the biomass firing in the first figure. The gas generated can be used in gas turbines. The figure in the second row shows the use of gas turbine and steam turbine for power generation. It is typically known as combined cycle. In the right-hand side figure, one can see the conversion of waste to energy plant. Hence, biomass gasification, combined cycle, power plants and waste to heat recovery are other applications for combustion. So far, we saw various applications. Let us see some of the fundamentals or principles or elements of combustion in order to improve on our understanding in combustion. Here, we can see the basic reaction of methane and air reacting to form carbon dioxide and water vapor. As we know, stoichiometric condition means chemically correct amount of air is supplied and hence the combustion is complete. One can write reaction balance equations for hydrocarbon fuel burning with air. The alpha and beta represents amounts of carbon and hydrogen present in the fuel respectively. From the reaction balance equation, one can get 1 kg of methane needs about 17.2 kg of air for complete, that is stoichiometric combustion. 1 kg of diesel needs about 14.5 kg of air and 1 kg of petrol need about 14.7 kg of air. On the other hand, 1 kg of H2 needs about 34.3 kg of air. The element balance and molecular weight is needed to obtain air-fuel ratio. The molecular weight of common elements is presented in the table. As a summary, reaction showing chemical element balance is helpful on estimation of air requirement. Once the reaction occurs, it releases heat. Let us see heating value. Calorific or heating value. When fuel is burning with oxidizer, it releases the chemical energy as heat energy. Amount of heat energy released is represented with heating value. Generally, one of the byproduct from hydrocarbon fuel is water vapor. To produce water in the vapor form from the liquid form, latent heat is to be supplied. On the other hand, one cools water vapor, it becomes liquid form by releasing latent heat. Hence, heating value may be categorized in higher heating value. One can get higher heating value by accounting the heat released when cooling the exhaust to room temperature. Calorimeters, buoys, junkers and bomb are used to measure heating value of fuel. As a note to remember is that heating value refers to lower calorific value unless specifically mentioned. The other important parameter is adiabatic flame temperature. One can abbreviate it as AFT. AFT is the maximum possible temperature due to combustion. It is estimated under the assumption that there is no heat or work transfer to the system. By equating enthalpy of reaction to enthalpy of the product, one can get AFT. Typically, the adiabatic flame temperature for natural gas is about 2343 Kelvin. Generally, thermocouples are used to measure exhaust gas temperatures. Here, we can see another important parameter known as equivalence ratio. It is defined as ratio between actual fuel-air ratio and stoichiometric fuel-air ratio. Phi equal to fuel-air ratio divided by fuel-air ratio at stoichiometric condition, or phi equal to air-fuel ratio at stoichiometric condition to actual air-fuel ratio. If phi is equal to 1, then it refers to stoichiometric condition. If phi less than 1, then it is lean mixture. If phi is greater than 1, then it is rich mixture. Equivalence ratio is one of the important parameters used in analysis. Let us see combustion regions with respect to lean or rich mixture condition. Flammability limit. The plot shows the extreme mixture conditions at which impossibility of ignition and combustion. It is represented with equivalence ratio phi. Too lean fuel or too rich fuel cannot burn. Hence, it is important combustion controlling parameter. We have just introduced some parameters. Let us see different types of flames. One can get different types of flames by directing air and flow path and the velocity of flow. Let us first see premixed flames. Premixed flames. When air and fuel is mixed well before the combustion, it is known as premixed combustion and the corresponding flame is referred as premixed flame. We can see premixed flame in the top diagram at the right hand side. Fuel and air mixture is coming out from two nozzles. When ignited, there are two flames represented with reaction zone. The exhaust gas leaves perpendicularly. Practical examples are 1. Petrol engine and 2. Gas stoves. In a petrol engine, the fuel and air is mixed in the intake manifold and sent to the cylinder. Hence, the combustion is of premixed in nature. In a gas stove, the burner system is designed in such a way that some amount of air is mixed to form blue color flame. Generally, premixed flames are of blue in color. Also, if no further orange flame is not seen with oxygen environment, we can say that the combustion is complete. On the other hand, in the case of diffusion flames to occur, air comes from one path and fuel comes from another path before combustion. The mixture is formed due to intermolecular diffusion in the reaction zone. As the hot gas moves away, fuel and air come again to form mixture in the flame region. In a diesel engine, the fuel is sprayed into the compressed air. The mixture is not homogeneous in nature. Air and fuel to be mixed in the combustion zone. In most of the applications, diffusion combustion takes place. Generally, in the diffusion flames, the color changes through red, orange, yellow to white as temperature increases. Here we can see the laminar flames. As we learnt in fluid mechanics, as the flow speed is less, the Reynolds number is less, then we can say the flow is laminar, meaning that layer over layer. In combustion also, we can see some similar nature. When the flow speed is less, clear flame with no much oscillations is noticed. Such flames are referred as laminar flames. Further, as equivalent to fluid mechanics, the flame also take a transition from laminar to turbulent. By and large, we can say, laminar flames are of mostly experimental nature with limited applications. On the other hand, turbulent flames are violent. Fluctuation in velocity is typical nature for turbulence. Sometimes we can see cell structure, as seen in left side of middle figure. Flame gets wrinkles and the flame area gets increases as seen in first left hand side figure. By and large, most of the applied flames are of turbulent in nature. Lifted flames. On further increasing the flow velocity, the flame can lift off from the mouth of the burner. One can clearly see the lifted flame in the picture. In case of lifted flames, local flow velocity is more than local flame speed. Flame may blow out on further increasing the flow velocity. In many industrial applications, flame stabilizers such as V-gutters are provided to hold the flame. In a summary, we can see laminar to turbulent flames with lift-off to blow-off condition with increase in flow velocity. The blowout occurs due to high velocity, less mixing and local strain. Now, let us see the experimental setup and demonstration of obtaining various types of flames.
Dear students, welcome to the experiments on flames. So this unit is generally called flame propagation. So this experimental setup consists of two different experiments, namely one is on Bunsen burner to know various types of flames, and the second one is on flame propagation unit to estimate laminar flame propagation speed. Just I will explain various parts and components present in the experimental setup. So it has fuel supply unit. This is the fuel cylinder. From the fuel cylinder, gas is passed through the rotometer. So from here the gas is coming to rotometer. From the rotometer, gas is passed through this metal tube and it is passed through the valves and to this flame propagation experimental unit, and the fuel is also passed through another tube. From this tube, the fuel line is coming to the Bunsen burner through this on and off valve, and so the fuel alone can able to come through this Bunsen burner. Now we will see the air supply. So the air is compressed in the air compressor, and the compressed air is passed through this line and it is sent to the air tank air is passed into the air tank on the table. It also has the pressure indicator, and there is a valve to send the amount of vary the amount of air into the experiment, and this unit you can able to see airflow meter. So how much air is passed through this tube can be measured or will be shown in the airflow meter unit. So the air is coming to the one experiment through this valve for flame propagation tube, and another one air is coming to another line is air is coming to the Bunsen burner. Air is coming through this tube and it has been regulated through a valve and sent to the Bunsen burner. Now let us start the experiment on Bunsen burner. First you close the air regulator valve tightly and allow the fuel alone and switch on the fuel line. If you switch on the fuel line, fuel alone will pass through the Bunsen burner tube and fuel will be coming up. Because there is no ignition, it will not see the flame. Ignite this gas, you can able to see the flame here. Now we will see the diffusion flame. Let me open the fuel line. Let us start the experiment for diffusion flame. Let me open this fuel line. The float will move to an extent, say till 0.5 you keep it there, and then so this is the typical diffusion flame. You can able to see the brown color nature or orange color nature. The fuel is coming here and air is diffused from the atmosphere. So this is called a diffusion flame. Now let us see the premixed flame. Now fuel is coming from this fuel line and air is coming from this. Air is we are allowing to start to come. So if I open the air line, air and the fuel is premixed in this. You can able to see this is the typical premixed flame. You can able to see the color has been changed from this orange color to the violet color. Orange color is typically for a diffusion flame. So this is the premixed flame. So we have seen so far diffusion flame as well as the premixed flame. Now let me look into two different things. One is on lifted condition, another is the blowout condition. In the lifted condition, the flame will be get lifted off from the Bunsen burner mouth. So if we increase the airflow rate, so we are trying to see that the flame is getting lifted off. This is the lifted flame. You can able to see the flame is started slightly dancing that. So this is the lifted flame. So if I further increase the airflow rate, then the flame will be lifted off and gets to blowout. This is the blowout condition. So in summary, we have seen a diffusion flame which is more or like a laminar type of flame. So laminar and the diffusion flame we have seen. Then if we increase the airflow rate, then we can able to see the color is changing from orange color to blue color. This is typically a pre-mixed flame. Air and fuel is mixed, so you can able to see the pre-mixed, and you can see lot of violence here, that is flow rate is increased. So this is the typical nature of the turbulent flame. So now we know laminar flame, turbulent flame, pre-mixed flame, diffusion flame, and if we further increase the airflow rate, the flame try to get lift off from the mouth. So this is the lifted flame. So once if I further, this is the lift off thing, you have to adjust the airflow rate very closely so that you can able to see the lift off height. and then if I further increase, the flame will get to blow off conditions.
As a summary, the left-hand picture shows Bunsen burner. In our experimental setup, we can vary the air and fuel flow rates. Hence, we got various flames and lift-off and blow-out conditions. Now, let us see and use flame propagation unit to determine laminar flame speed.
The Bunsen burner experiment. Now let us start the laminar flame speed experiment.
Let us start the experiments on laminar flame speed. Laminar flame speed experiment. It is a simple experiment to understand few aspects of combustion and flame propagation. Let us first introduce theory and importance before conducting the experiments. The laminar flame speed is one of the important property of fuel-air mixture. Property means here is it has one value or it is constant. It is mainly due to the flow is at laminar condition. Further, laminar flame propagation is a fundamental problem in combustion. On the other hand, it is easy to conduct experiments to measure laminar flame speed. In essence, laminar flame speed is a basic parameter either to determine turbulent flame speed or flashback. Let us see some theoretical background for laminar flame speed. Analysis of attached flames. Let us look into Bunsen burner flame more carefully. One can see the inner core, which is nothing but premixed flame. Remember, what we are going to measure is also laminar flame speed. It is also premixed type. The right side figure shows velocity vector in the inner flame. Here, laminar flame speed equals to normal component of unburned fuel-air mixture velocity. Now let us analyze the case reasons for lift-off and flashback. Reasons for lift-off and flashback. We have seen lift-off already. Flashback is the new phenomena we are studying here. The relative velocity between laminar flame speed and unburned mixture velocity is an important parameter to understand flashback and lift-off. When the flow velocity is lesser than laminar flame speed, then results in flashback. When the appropriate component of flow velocity is more than laminar flame speed, then there is a possibility of liftoff. Imagine a situation in aircraft gas turbine engine when the liftoff towards condition is close to blowout. By and large, both flashback and liftoff lead to safety issue. Let us consider a tube consisting of burnable or combustible air-fuel mixture without any movement. Suppose if I ignite at one end, there will be flashback action, that the flame propagate from burned mixture to unburned mixture. The reasons for flame propagation may be thermal propagation. The mixture is heated by conduction to the point where the rate of reaction is sufficiently rapid to become self-propagating. Or diffusional propagation. Diffusion of active species such as atoms and radicals from the reaction zone or the burned gas into the unreacted mixture causes reaction to occur. In reality, both diffusion of heat and active radicals are happening. Theoretical estimation of laminar flame speed. On further analyzing the flame structure, one can estimate theoretical flame speed with one-dimensional assumption. For this case, rate of reaction to be known in the model during estimation. Since the derivation is slightly at higher level, one need to know the results at this time. The value to be remembered is about 40 cm per second as laminar flame speed of methane. Let us conduct the experiment and measure the laminar flame speed.
For this laminar flame speed experiment, the fuel is coming from the same fuel tank and the fuel is passed to the rotometer and the fuel is coming to this tube, and if I open or close, the fuel will be passed inside this tube. Air is coming from the air compressor and the air is stored inside this line to the air tank. So if I open this wall, the air is passed to the airflow meter and the flow is coming through the tube, and this is the wall to control the air inside this chamber. So this red color chamber is basically a premixing the air and the fuel. Once air and fuel is premixed, it allows to flow through this entire tube and the air and fuel mixture will pass through into it. And there are two indicators. One is here, that is the flame indicator. Another flame indicator is present at the entrance. There is the another flame indicator. The length between these two sensors, flame indicator sensor, is about 110 centimeters. So there is a igniter. This igniter, if I ignite, if the flow inside this one is stopped, which means the walls at the front, if we stop, there won't be any flow on this direction. Whatever the stationary air and fuel collected in the tube will be get ignited and the flame will goes back. So this is the starting point of the flame and the end point of the flame at the entry. So we need to know the time taken to travel the flame from this sensor, first sensor. So the distance between the first sensor and second sensor is 110 centimeters. So once if we know the distance and the time in the timer, time measured in the timer, we can able to calculate what is the velocity by distance by time. This flame velocity is the characteristics of the fuel and air mixture. So it is some sense or not, it is like a property of that mixture. Now let us start the experiment. We allow the first fuel line. So let the fuel will be started here and allow the fuel to flow through, and air is also allowed to flow through. Now switch on the power supply. You switch on the console. You can see the airflow rate meter and the timer meter. Simultaneously open these two valves. Continuously give the ignition. You can see the ignition sound there, igniter sound. And while simultaneously closing the valve, you see that the flame is started and propagating from this end to this end. So you need to simultaneously open air and fuel. At the same time you need to give the ignition at the other end. So I am just opening this. Immediately I have to close this. You see the nice flame coming inside the one. So now take down the reading for the timer. The timer reading is 1.039 seconds and the flow reading is 34.4 cubic centimeter per second.
One can also get laminar flame speed at various equivalence ratio. The peak speed is close to stoichiometric condition. Thank you for your attention. Hope your mind got ignited to learn about combustion and its applications with giving importance to the experiments.
At MSR UAS, we spark your imagination unlike any other.